All right, so we're going to work on some horizontal circle problems where there's an angle, which makes them a little bit more difficult. Here is a conical pendulum where you have something attached to a string, and instead of moving it left to right like a regular pendulum, you just move it in a small circle so that the string makes the shape of a cone. We're going to go ahead and watch that right here. Thankfully, we got Uncle Jesse from Full House to do this demonstration. There you go, a conical pendulum. So exciting. Okay, so conical pendulums for us are going to have a couple of key features. One is that there is an angle right here that's made with the vertical. Now, the reason why that's important for us is because ultimately we would like to take the tension that's in this string and turn it into an upward part and a forward part. So theta goes right there. This component is going to be t cosine theta, and then this component is t sine theta. Now the weight goes down, mg, and so we get two equations. First, we know that the weight is going to be equal to t sine theta, or I'm sorry, t cosine theta. So t cosine theta equals mg. Now the second equation we get is that t sine theta is the force that always points towards the center of the circle, no matter where we're at. So t sine theta becomes our centripetal force. So we set it equal to mv squared over r. Now we can do a clever thing with these equations where we divide them by each other. And if I divide t sine theta by t cosine theta equals mg, then two things happen. First, I get rid of the tension, and I get tangent theta on the left side. Then also I get rid of the mass, and I have v squared over rg on the right. Now I can use this to solve a bunch of different things in the problem, including what the angle is, the velocity, the radius, and if you're on a different planet or something, you could use this to figure out what the acceleration due to gravity is. So let's do an example. Here you have an 8-kilogram toy attached to a string and it's swinging in a circle. The angle the pendulum makes with the vertical is 30 degrees, and the length of the string is 1.2 meters. We're going to find the tangential velocity of the plane. Okay, so this is like a little toy, and the airplane is attached to the string, and it's kind of flying in a horizontal circle. Now we know that the angle with the vertical is this thing right here, and we're going to call this theta, and theta is 30 degrees. And we're going to use that to first figure out what the radius of this particular circle is that the airplane is making. Now, to find the radius, we need to use the fact that the length of the hypotenuse, or the string, right, is 1.2 meters, and therefore that side that the radius is going to be will be 0.6 meters times sine of 30 degrees. I'm sorry, 1.2 meters times sine of 30 degrees. And 30 degrees is a half, so half of 1.2 is 0.6 meters. So that's our radius, 0.6 meters. Okay, now let's take a look at the forces that are acting. You've got the weight force down, you've got tension T up, and that tension is going to be turned into an upward component where theta goes there, and so we'll call this t cosine theta, just like in our example problem, and then this one is t sine theta. Okay, now we know t cosine theta is equal to the weight, and we know that t sine theta is the centripetal force, so when we do t sine theta equals mv squared over r, and then we divide that by t cosine theta, we get the exact same thing that we had before, tangent theta equals v squared over rg. Now for this problem we want to find the tangential velocity, so we solve for the velocity by multiplying both sides by rg. So we're going to get v equals rg tan theta, and we need to take the square root. So once we put in the radius of 0.6 meters, the acceleration due to gravity of 10 meters per second squared, and then tangent of 30 degrees, we are going to get 1.86 meters per second. So that's the velocity. All right, now we're going to talk about banked curves. Banked curves are where you have a car that is on the angle of an incline. Let's take a look at an example. All right, here we have a car on a banked curve.
I don't want to go up there. I want to go up there. I'm going to try and lift it up the banking on this one. Here we go.
Okay, so there we go. We got a banked curve. Now, for a banked curve, you will always think of it as an inclined plane. Okay, so think about almost like you're slicing part of that curve, and you're going to look at the car as it's going on the front end. So let's draw the car like this. You got your little tires right there, and you're going to put the windshield. There you are. You're really excited. You're driving the car. You got all your friends and family and your pets in there. Headlights, little grill. Congratulations. Now, the goal for a banked curve problem is we're going to put the weight force down and the normal force up at an angle. But rather than take mg and turn it into a sine and a cosine theta, you'll find that for most of these problems, you are going to want to take the normal force and turn it into a y and an x component, where theta belongs here because this is the angle of inclination. And so if I think about how the angle of inclination would be right here, then this is like, like alternate, what do they call them? Alternating interior angles or something like that. So there you go. The adjacent side, n cosine theta, is going to be here, and then n sine theta is the opposite. Now, from this, you should see that n cosine theta and mg are equal. So n cosine theta equals mg. N sine theta then becomes our centripetal force. Most problems that you deal with banked curves, there's not going to be friction. There's just going to be some force that's up at an angle, and the part of that force that's always, unbalanced is what points towards the center of the circle at every moment. So n sine theta for us is our mv squared over r. Now we do something pretty much the exact same as with the conic pendulum here. We divide n sine theta by n cosine theta, and then v squared over r by mg. So we get rid of the normal force, we get rid of the mass, which means you don't actually need to know what the mass of the car is to solve these problems, and you get tan theta equals v squared over r times g, which is exactly what we had before. Now, here is a practice problem. See if you can solve this problem on your own. Press pause, and then when you've gotten as far as you can, come back and we'll do a solution. Okay, so press pause. Did you press pause? Okay, great. Now let's talk about the solution. So you need to do the exact same thing. You draw your inclined plane. You've got your car. I'm just going to draw it as a box for right now because I'm too lazy to draw my car, even though I'm really good at it. You got your weight down, your normal force. Congratulations. You know that this is adjacent, so this becomes n cosine theta, right? And then this is n sine theta, just like before. Hopefully you drew that free body diagram. If you didn't and you just copied equations, the likelihood of you getting questions right is pretty low, so you should stop. Now, n sine theta is equal to mv squared over r, right? Because it is our centripetal force. Cosine theta is balanced by the weight. So we've got n cosine theta equals mg. We're going to divide those two so that we get the exact same thing that we had before. Tangent theta equals v squared over rg. And for this problem, we want to figure out how fast the car must be going so that it does not slide down the incline as it makes the turn. Basically, this just means without friction. You're not including friction. If you were including friction, you would need to draw it, break it into an x and y component, and use the static coefficient of friction to adjust both of these things. But in this problem, we don't care. In fact, we don't care about the mass, and we don't care about the coefficients whatsoever. They're just there to throw you off. What we do care about are the angles, the radii or the radius, and this is unimportant too. All right, so to figure out how fast, we just need to find v squared. So we take this whole thing and we rearrange to find v, which you're going to get v is the square root of rg tan theta. You plug in your radius of 10 meters. Your acceleration due to gravity, we're going to use 10 meters per second squared, and then tangent of 30 degrees, and you are going to get 7.598, so we're going to call that 7.6 meters per second, which is pretty slow, but it's reasonable for this small of an angle and small of a radius. Okay, now let's talk about a problem that doesn't actually use a bank for this angled force. Instead, what we're going to have is an airplane. So here you have an airplane traveling 250 meters a second, flying level when it enters a banked turn with a radius of 950 kilometers. what will the angle of the banked turn be? Actually, you know what? This 950 kilometers, that's going to give us an absurd angle. That's like a fraction of an angle. Let's just go ahead and say 9,500 meters, so 9.5 kilometers. Okay, 9.5 kilometers. That's the radius that you want. All right. At this point, I want you to try and solve the problem. Pause, try and solve, and then come back for the solution. You pressed pause, or you didn't. You're just waiting. Please don't lie. You don't want to be a liar. Come on. You always try to just take the equations and use them in the problems, and it doesn't work. You know, you got to try it on your own first. Physics is about doing. Okay, here we go. So in this problem, you've got your airplane. I'm going to draw the airplane. It's going to be fantastic. There you are. Here's your dog and everything. It's really fun. The front of the airplane. Congratulations. Then you got these two little wings, and then pew, pew. You got this little side in the back. You're flying. It's great. And the thing that you're pushing off of to sort of both hold you up against your weight and also cause you to turn is some lift from the air, some force that you're pushing off of the air. It's like you're constantly throwing air underneath of you so that you can get that lift force up. Sometimes we call this F lift. I'm just going to call it F. Now, the point is of this problem is to figure out what the angle will be, and the angle will be relative to the horizontal. So if I draw what the angle of the airplane is, the angle is going to be here, and therefore the angle we use to orient this force goes there, right? Alternating interior angles. I think that's what it's called. So this lets us turn F into an upward component. Okay, so that's going to be F cosine theta, and then a leftward component, which we will call F sine theta. Now, F cosine theta and mg, those two are equal to each other. So we would write F cosine theta equals mg. And if you hadn't guessed, F sine theta is our centripetal force. So we'll say F sine theta equals, that's right, mv squared over r. Wow, what a terrible 2. Okay, so mv squared over r, and this hopefully is starting to make some sense. You would get rid of the force and the mass, and you're left with the same relationship. Tangent theta equals v squared over rg. Now to find the angle, we just need to do tangent inverse of v squared over rg. That's what's going to give us theta. So tangent inverse of the velocity, 250 meters per second, the whole thing squared. Then you divide it by the radius. We're going to use 9.5 kilometers, so we need to convert that to meters by multiplying it, by 1,000. So 9,500 meters times 10 meters per second squared. And when you put this into your calculator, you should get 33.3 degrees. Congratulations. You did good.